professor is traveling out of the country for some conference, and he asked me to give a guest lecture in his class today. So my name is Yan Dong, and I'm a second-year PhD student in his group. And today I will give a brief introduction to the hardware accelerators for deep neural network. And this is a very hot research topic these days. And if you take a look at those papers published in the EDA or Computer Architecture Conference, a lot of them are talking about the hardware accelerator from both universities and from industry. So, and in this lecture, maybe you are unfamiliar with some of these concepts because I think you guys are second year or third year undergrad students. But don't worry, I'm just giving you a brief introduction. And if you could take more courses on a specific topic if you are interested. And this is the outline of my lecture. So in the first part, I will give you a brief introduction to artificial intelligence, which is called AI. And in the second part, I will briefly talk about the deep neural network. The deep neural network, DNN, is the most popular and successful approach for AI. And I will introduce some basic concepts on the DNN. It will help you better understand what is needed to accelerate the deep neural network processing. And in the third part, I will talk about some specific types of accelerators and give you an overview of those DNN accelerators. In the fourth part and fifth part, I will pick some specific accelerator design, such as the graphic processing unit and CMOS ASIC at Google's TPU, and the new technology called computing memory to discuss. So first is the introduction. So the AI is defined as the capability of a machine to imitate intelligent human behavior. That means AI do some intelligent work, not a labor work like carrying a box. So recently AI has made huge achievements in many fields. And there are three examples. The first one is the self-driving car. And the AI is trying to control the car with some software algorithm without a human driver. It can react to the change of environment. Basically, in the self-driving car, there are some cameras to detect the objects and give those information to the algorithm, the AI, to make the decision. And there are many companies are working on this, such as Tesla and Waymo. The related field in AI is called reinforcement learning. Then you can take the CS 7642 on this topic. And also another thing is that to detect those objects on the road, we usually use something called LiDAR, the light detection and ranging. This is related to some optics field, and it's the hardware design. The second example is Google Pixel. It can do a real-time translation when you are talking with some other people. So this requires the AI to understand human language, and this field is called natural language processing, NLP. And you can take the CS 4650 to know more on this natural language processing. The third example is to detect pneumonia from X-ray imaging. This is related to the image classification, and you can take some courses on deep learning, and they will talk a lot on this image classification problem. And the AI is driven by some algorithm. The most popular algorithm is a deep neural network. There are multiple types of neural networks. The first one, the most simple one, is called multi-layer perceptron. Basically, it has some input, and we do some computation and get the output. The output can be some some labels of the images of your input. For example, if you input an image of a dog, and they can give you the corresponding label of this input. And the second one is the convolutional neural network. And this is usually used for the image classification. And also, for language processing, people usually use the recurrent neural network. The recurrent neural network has some feedback, so it can handle something that are correlated to the previous input, such as the language or some text. And later I will give you a brief introduction to the MLP and convolutional neural network. So one problem for the deep neural network is that it's going deeper and deeper for better performance. The state of the art deep neural network usually have tens or even hundreds of layers. So that's why we call it deep neural network and deep learning, because it has many layers and the network is very deep. When the neural network goes deeper, the number of parameters also increase. For example, in the ResNet, we have tens of millions of parameters, and so the huge number of parameters needs a large space for the storage, which is very challenging, especially for the applications on mobile phone. And also, as the neural network goes deeper, the computing becomes very complicated. It consumes a lot of energy, and also the processing speed is large, and so that the processing speed is very slow, and so the latency is high, and the high latency can make some real-time applications, such as the self-driving car, to be very challenging. So a summary of the challenges in the deep neural network processing. The first is that since there are a lot of parameters in the deep neural network, it requires a large memory space for storage. And there are some solutions at the algorithm level. The first one is to compress the neural network, and the second approach is to do a quantization. That means we transform some high precision number to a low precision number. For example, some network use only 8-bit weight instead of the 32-bit floating point weight to reduce the storage space. And another challenge is the low processing speed. Because there are a lot of multiply and add operations involved in the deep neural network processing. And those are very time-consuming. So it's very challenging for the real-time applications if your processing speed is low. For example, the self-driving car needs to react to some emergencies on the road immediately. So in this case, the processing speed is very important. And another thing is the high energy consumption, because on the edge device, such as your mobile phone, the power budget is quite limited. So it requires that when we are processing the deep neural network, it will not take too much energy. So the hardware accelerators are designed to improve the processing speed and the energy efficiency. And this is the introduction to AI. And in the second part, I will introduce some basic concepts of the deep neural network. It can help you better understand the challenges in the deep neural network processing and how to accelerate the processing of deep neural network. I will briefly talk about two types of neural network. One is the MLP, multi-layer perceptron, and the second one is the convolutional neural network. They are the most common and popular networks. So the first is multi-layer perceptron. This is the most simple network. First, and this figure shows the structure of a three-layer MLP network. So first, you see that there are some nodes in the network. It is recording neurons. Basically, it's just some numerical values. The first neuron layer of the network is called the input layer, and the input, such as image or some text, is fed into this input layer, and the intermediate layer is called a hidden layer. The values, the neuron values in the hidden layer is calculated based on the input from its previous layer. And in this example, there is only one hidden layer, but in an actual network, there can be several hidden layers. And the last one is the output layer. It gives the inference results of the neural network. For example, for the image classification, it gives the label of the image that you input into the network. And we notice that there are some lines that connect those neurons. We call it synapse. And the synapse is the weight that represents how much impact one neuron has on the neurons in the next layer. In the MLP, one neuron is connected to all the neurons in the next layer. So it is also called a fully connected network or fully connected layer, FC layer. For example, this neuron in the first layer is connected to all the 4 neurons in the next layer. And the same thing for these 2. And mathematically, each neuron layer is represented by a vector, which is one-dimensional, such as this x1, x2, x3, y1, y2, y3, y4. And here, and the synapse that connects those neurons are represented by a matrix. So here we have 3 input neuron and 4 output neuron. So they are connected through a 4x3 matrix, like this. And in the we also call this matrix weight matrix. And in the weight matrix, each element represents the weight that connects 2 neurons. For example, the W11 is the weight that connects the first input neuron X1 to Y1, and the W12 it connects the input neuron X1 to the output neuron Y2. To get the value of those output neurons, the input vector X is multiplied with the weight matrix W, and this operation is called a vector matrix multiplication. So for the vector matrix multiplication, basically the first row is multiplied with the vector, and we get the output neuron, the first output neuron Y1, and then we multiply the second row with the vector, and we get Y2. And then that's how we get each output neuron value Y1 to the Y3 to Y4. And if you take a look at those equations, there are 2 types of operations. One is the multiplication operation, and the second one is to add up those results, and we call it accumulate. So basically, these multiply and accumulate operations are the dominant operation types when we are processing a deep neural network, and we call it a MAC operation. And the drawback of the fully connected layer is the scalability. The size of the weight matrix is the number of input neurons times the number of output neurons. So the number of weight parameters will be increased drastically if you increase the number of input neuron and output neuron. So the scalability is an issue. To solve this problem, people propose the convolutional neural network. In the convolutional neural network, the input of the input layer is called an input feature map, IFM, and the weight matrix is replaced by filter. The filter is just a small matrix, and the output neurons that we obtain is called the output feature map. And to get the output feature map of the convolutional neural network, the filter is interacted with just a small area in the input feature map, and get one output neuron here. And also the filter will be shifted, will be moved on the input feature map, and we get different output neurons. For example, here we have a 3x3 input feature map and a 2x2 filter. First, the 2x2 filter is multiplied with the first four elements, the x11, x12, x21, x22, and get the first output neuron in the output feature map. And then it moves to the next four input neurons, and we get one output neuron. And that's how the CNN works. So basically, the filter is like a feature extractor that can extract some local features in the input feature map. For example, here is a convolutional neural network, and those pictures are the feature maps that it obtained after each layer of filters. So for the first few convolutional layers, it got some low-level features. Basically, it's the outline and the edges of your input image. And this is similar to how human recognize an image. And for the deeper layers, it finds some more abstract or high-level features for making the decision. And those features are very difficult for humans to understand. And if we take a look at how each output neuron are computed, we can see that for convolutional neural network, still each output neuron is obtained with this multiply and accumulate operation, the map operation. So it's still dominated by map operation. And in a real convolutional neural network, those filters and input feature maps can be high dimensional. It can be 3D or even 4D. But it can still be converted to the vector matrix multiplication, which consists of many map operations. So for the CNN, still the map operation is a dominant type during its processing. And to design the hardware accelerator for the CNN, we need to find the features of its computation node and do some optimization to this. I think the first feature is that there are low data dependency between each output neurons. For example, to get this the second output neuron, 012. We don't need to wait until the computation of the 011 is finished. We can do these two computations at the same time. And so, one feature of the CNN computation is that it offers a high computational parallelism. That means we can get those output neurons at the same time, and it can help us reduce the processing latency. And another feature is that if we look at this equation, we find that to get both 011 and 012, basically they are using the same filter weight, the same weight. And so another point is that we can try to reduce this filter weight so that we don't need to fetch it from memory many times, which consumes a lot of energy. So this weight sharing gives us opportunities for the weight reuse and can help reduce the energy consumption during the DNN processing. And besides, when we are computing the different output neurons, we notice that part of the input features are the same. For example, for this 011 and 012, they use two input features, x12 and x22. And therefore, we can add 012 means x12 and x22. This is called the input feature map sharing, and it's also reduce the energy consumption to fetch the input feature map many times. So a summary for the deep neural network. And so first, the computation mode for the deep neural networks are mainly vector matrix multiplications. They consist of many multiply and accumulate operations. And for the features of the DNN processing, first, it has a high computational parallelism, and this could help us reduce the latency during the computing. And another thing is that during the DNN processing, there are many opportunities for the weight and input feature map reuse, and it can help us reduce the energy consumption to fetch the data from memory. So in the first two parts, we know some basic concepts of AI and the challenges in the DNN processing. And here I would like to give an overview of the DNN accelerators. So first, the DNN accelerators have two different target domains. One is deep learning in the cloud. Since the deep neural network requires a lot of computational resources and a huge amount of training data, so typically, and also it needs a high precision training. So typically, it's trained in cloud cluster that consists of many GPUs. For example, this Google Cat, it's an algorithm to recognize a cat face in the YouTube video. It uses 16,000 CPU cores in a cloud, and it takes about 100 kilowatts in 3 days to train the network. And for the Microsoft ResNet, it's used for the ImageNet classification to use 8 GPU accelerators.